Hi, this is Manuel from Entagma. Welcome to another Houdini tutorial. Today we want to talk about something we've seen a lot recently, that is 3D knitting. But before we create a three-dimensional knitted model, let's see how we can understand the principle of knitting in 2D. Here you see knitted loops. Unlike a woven surface that is made up of a multitude of yarns, a knitted fabric is made up of only one yarn. This yarn is bent into loops and these are intertwined and form the fabric. How can we create something like this in 3D? Well, basically it's difficult to intertwine just one long polyline, so maybe we can make use of the symmetry of the structure. If I draw circles above this and overlay both, you see that we have a distinct symmetry to the pattern. And that means we can create just one knitting loop and then duplicate it to create a two-dimensional knitted pattern. Once we have this, we can then project this two-dimensional knit to a three-dimensional surface. We make use of the same technique as texture mapping. For most 3D objects, we have a UV space. The UV space is a parametrization of the three-dimensional space, meaning it transforms three-dimensional space to two-dimensional space and vice versa. So, having UVs, we can use the two-dimensional knitting pattern to project it to the three-dimensional form. Here we have the UV map of the three-dimensional object on the left, and the orange dot is the same location on the left in three-dimensional space and on the right in two-dimensional parametric space. If we now put our knitting, symbolized by one knitting loop here, on top of the UV map, and then look up the UVs, we can sample the three-dimensional point positions and thus transform this pattern to the three-dimensional object. But how can we gather the necessary UV information? Well, we can use ray tracing, because we have to find the primitive and the barycentric coordinates of the primitive to be able to transform a two-dimensional point to the three-dimensional representation. So we create just a ray for every point of our knitting loop, shoot it down into the UV space, and you'll see how we will accomplish this in practice in Houdini just in a second, and look up the three-dimensional point. And then we can just put the two-dimensional loop in 3 dimensions. So let's just dive into Houdini and try this out. To start, please open the file knitting start 01 hip that you can download beneath this video. I already created a simulation of some balls falling down and imported this as an Alembic archive, and I created a knitting loop, as you can see in a second. Here is the simulation of the ball that I want to eventually transform into knit, and if we dive into this knit master object here, make this visible, you see that I have my circle here that I already duplicated to create my basic symmetry pattern, and I already used this symmetry pattern, if I overlay both, to create a curve that is just half of one knitting loop. Here you have this curve. To create a two-dimensional knit pattern from this half curve, first append a mirror. And let's mirror this loop to form a whole loop. You see, this is just a polyline, and we want this to be one long yarn. So at the moment we have two primitives. If I make primitive numbers visible, you see I have primitive 0 and primitive 1, but I want to have one loop, so I use a join operation that can be used to join two curves into one, and now I have only one primitive. And now let's convert this to a NURBS curve. Like so. NURBS curve. And it is smooth. This is our basic knitting loop. And now we can copy this over to form a knitted surface. Let's first copy an X, append a copy and transform. Copy and transform. And let's create 50 copies of this loop, and by trial and error I found out that 1.2 is the right number to put in translate X, and you see this gives me a long line of loops. But again, this is individual primitives and I want just one primitive. to make up this first yarn. So another join to a rescue will create just one long primitive. That is our first yarn. Now another copy and transform, this time in the Z direction. Again, 50 copies, and by trial and error I found 1.16667 is the right value to use here. And this gives me a nice knitted pattern. If I zoom in, you see that these loops are interlocking. That's because I drew my very first curve, such that exactly this happens. This is a little bit of manual work, but you have it in the file already. To finish off our knit surface, just append a resample, because later on we want to project every point, and thus we need a polyline instead of a NURBS curve, but it should be smooth. So I put a resample and I get a smooth polyline. And then I append a null, because the knit 2D is finished here, like so. The next thing is that we want to import a surface to project this 2D knit to. I already created an object merge. If I make it visible, you see I imported one of the balls from the Alembic archive. This object merge points to the Alembic archive and grabs one of the balls. But we cannot use it because it's a delayed load Alembic primitive. So the very first thing to do is to append a convert and convert this to Houdini geometry, in our case polygons. And now you see I have editable geometry. If I now press space and 5, you see that this ball comes with an UV map. It has 6 UV islands, and these will be used later for the projection process. But before we do this, let's append a normal, because it comes without normals. And what we want to do now is we want to transform this polygonal three-dimensional object to its UV representation in 3D space. Because we have knitting loops in 3D, not a texture map, we need the UVs to exist in 3D space too. That means what we want to do is to make every point exist in the spot of its UV coordinate instead of its position. Well, basically it's very easy. Let's just look up the UV coordinate of every point and then use this as its new position. But it's a little bit more complicated as the UVs exist on vertex level. If I go to the geometry spreadsheet, you can see that I have the UV attribute here on vertices. And as you know, every point can have multiple vertices. And here this is actually the case because we have multiple UV islands. That means some points share different UV coordinates. So we have to somehow unique the points that have different vertices attached. To do this, there is a very handy little node called vertex split. Let's use it. Vertex split. Vertex split looks at an vertex attribute, and whenever the vertex attribute deviates more than the tolerance between two vertices, it splits the associated points apart. That is exactly what we need. If we put UV here, what we now get is more points. Nothing visually changes, but if you middle click here, you have 368 points, and if I do the same here, I have 468 points, because vertex split created more points at the UV seams. I'm not sure if you can see this here, but here at the UV seam, I have now duplicate points. And that means that every point is left with just one UV coordinate. This can be used to our advantage. Now let's move the points to their UV positions. I do this with a wrangle. Append a point wrangle, and let's call it transform to UV, and press Alt-E to open the expression editor. The very first thing is to look up the vertex attribute UV for every point, because I'm working on points here, but the UV coordinates are saved on the vertices. But as every point only has one vertex left, that is possible now. So let's use the point vertex function. I create an integer called myVert and use the function point vertex that wants the current geometry stream, which is input 0, and the ptnum point number to sample. This function stores the vertex associated with the point ptnum in my vert. Now I can create a vector and call it PV for point UV. And this is just using the vertex attrib function that samples the vertex attribute. Again, geometry stream 0. The attribute is called UV. My vert is the vertex in question, and success is just a variable to store the state of the operation. That's why I quickly create an integer called success. Let's initialize it with -1. Not very important, but it's the clean way to do things. And now that we have that, let's set the position of the point with PUV x. And then in y we just use 0, because this is a two-dimensional space, and PUV y as our z-coordinate. If we now press apply and accept and make this visible, what happened is, we have a little error here. I missed a comma and an equal sign here. Now press apply and accept, no errors, and now we have the result. And that is our actual geometry turned into its own UV map. Now we have both laid out in two-dimensional space, our UV object and our knitting. But our knitting is way too large. We have to make it occupy the 0 to 1 space just as our UV map to be able to sample the position of the UVs and thus find the three-dimensional point position. So we have to transform our large knit. To accomplish this, we will use the bounding box of the knit, and we will use a VOP. So append a point VOP here and call it scale to 0 to 1 space, maybe, and make it visible, dive inside. And here inside we use the bounding box node. The bounding box node just spits out two vectors, and these vectors are the minimum and maximum corners of the bounding box of the incoming object. In this case, this is just the object itself. Now, these two vectors are minimum and maximum, but we are only interested in the x and z components. So use a vector to float to split the components apart, and append one vector to float to the min. With Alt, you can just duplicate it. With Y, you can cut the wire, and then 1 to max. Now we have the float component of the vectors, and we just duplicate this again and use it to split the position apart, because now we want to fit it. I create a fit node for this, fit range, and first let's care about the x component. So we want to fit the x component of the position between the minimum and maximum value of the bounding box. So let's use the minimum x component for the source min and the maximum x component, for the source max. And then let's do the same thing, but for the z component. So z component of the position, then use the minimum z component as source min and the maximum z component as source max. Now we have the x and z components fitted between 0 and 1. But to set the position, we need a vector. So let's transform the individual components back to a vector with float to vector. And let's use the remapped component for x and z. And for y, let's just use the original component from the position. And now let's connect this. And you see that all these loops are now transformed to the 0 to 1 space. If I zoom in, you see they occupy the 0 to 1 space in x and z, but in y they just kept their original height, which is a little bit high. So let's just append a transform and scale them down in y to 0.1, say, like so. Now we have nice knitting loops occupying the exactly same space as our UV map here. In our case, these islands don't fill the 0 to 1 space, but if you import a different model, it could be the case that this entire space is filled. In principle, we are ready now to do the projection, but we have one problem left, and that is the projection will only work where there are actual UVs. And this is not the case here, for example, in these gaps. So we somehow have to cut these loops, these knitting loops, and throw them away where there are no UVs. What comes into mind is to create a Boolean operation and just keep the loops that are inside of these islands. And that can be done. The thing is that the Boolean operation only works on polygons, not on open polylines. So we want to do a little detour to make the Boolean operation cut our open polylines. But first, let's create the cutting volume. So use a divide to turn these UVs here into outlines only by clicking Remove Shared Edges. That gets rid of all the internal edges. And now I can just use a poly extrude to make a volume out of these. Let's say 0.2, like so. Now I have this, and if I say output back, I have a closed form. And now let's transform this up a little bit, like so. Now I have cutting volumes for my Boolean operator, but my knitting loops still are open polylines. To make these knitting loops into something that the Boolean operator understands, I will use a poly extrude 2 and extrude these open polylines to strips of polygons. For this to work, I first have to add normals, so append a point wrinkle. Make it visible, and let's just add a normal attribute, add n, and that will be a vector, so curly braces, and the vector will be 0, 1, 0. What I do here is I just append normals that go straight up, because I intend to extrude all these open polylines just straight up. Now I can append a poly extrude to this side too, like so. Let's get rid of the normal display and give it a little height. And now we want to switch the extrusion mode to point normal and tell the poly extrude to use the existing normals we just set. And this gives us a nice extrusion just in Y up. It's too high at the moment because we want tiny little strips, like so. And this turns all my polylines in little strips of polygons that can be used with the Boolean operator. So let's just do this and create a bool. Let's wire these strips in one port and the cutting volumes here in the other port, and the Boolean will do its magic and will cut it. And this does not work on the open shapes, but it works on these strips. And now we have loops only existing where actual UVs exist, which is very good because then the projection will work. It's nice that we now have cut the loops, but eventually we'll need open polylines again. So we have to think about a technique to convert these polygons that are now cut into polylines again, which is a little bit tricky. The first thing to make this work better is to use a smaller distance here. Let's say 1/10 of what I had before, like so. Now I have very tiny loops, you cannot see it very good anymore. And on the Boolean I have a warning, and that is because I treat the input A as a solid, but actually it's a surface. If I switch this to surface, the warning is gone. And now let's convert these polygons back to polylines. I use the same divide node trick again to remove all the shared edges with remove shared edges and just keep the outlines. If I turn on wireframe, I see that I now have n guns. very complicated n-gons. I want to convert this back to open polylines. That can be done with the ends sub. The ends sub tells a polygon in Houdini how to treat the ends. And as closed polygons and open polylines are basically the same geometry type in Houdini, it's really about the end behavior that makes all the difference. Here it says close U, no change. If I say open, I now converted these closed polygons to open polylines. But one little segment that connects the last point with the first point is gone. So that's why I use unroll. What this does is it duplicates the very first point and makes the shape appear to be closed. That's all nice and fancy. I now have a nice open polyline again, but it's double. I have an outline of a polygon, but I only want one center polyline. So what I can do now is I can fuse together all the points. Let's fuse them together, use a higher radius, and that gives us back, if we pick the radius high enough, we need even more radius to this. And now all the duplicate lines are gone. It's all one line now. But be careful. The fuse sub fuses the points, but it does not fuse the vertices. And as this used to be a double line, now we have multiple vertices sharing one and the same point, and we have a primitive that appears to be a clean line, but in reality it goes back and forth between all the points. The order, unfortunately, is lost. So we have to think about a technique to bring the order back to this polygon here. The first thing we want to do is to write the information to which primitive the points belong onto the points, because we want to eventually delete all the primitives that we have at the moment. So let's use the connectivity sub for this. The connectivity sub evaluates the connectivity and creates a new attribute containing this connectivity. We write the connectivity to points and we call the attribute class, just the default. If we just quickly append a color, what we can do is we can go to points and then say random from attribute, and if we put class here, you can see that all the individual primitives have one color now, but it's a point color. So the points now know to which primitive they used to belong. Now, something a little harsh. Let's delete all the primitives. Just by putting a star here, all the primitives are gone. Just keep the points. Now we have just a mess of points with no connectivity info whatsoever. We will gather the connectivity info from somewhere else and then rebuild the polygons now. What we need is an order to the points. We want to recreate the primitives where there used to be primitives. That's why we wrote this connectivity info on the points. But we want the right order. The points that were created newly by the bool have to be put in the right order, which they are not at the moment. This geometry from the very first geometry stream comes to our rescue, because this geometry exists in 3D space and our points exist in the same spot as these primitives here. So we can use these primitives to order the points, and we can do so by using an attribute called curveU. If we go to the initial resample we created in the very beginning of this tutorial, we can turn on curveU attribute, and what this creates is an attribute on all the resampled points that is the position along the input NURBS curve. So whenever the resample creates a point at the beginning of the NURBS curve, it will give a 0 to this attribute, and at the very end of the NURBS curve it will give a 1. That means that now that we turn this on, even our reprojected loops have a curveU attribute on the points. Here it is. And that is important, because what we want to do now is we want to go back to our points without primitives and just look for their closest location on the original splines. Sample the curveU attribute and then sort these points by the curveU attribute. By doing so, we will generate the right order for all of these points, and then we can simply add a new primitive, which will give us clean, new, open polylines. Let's make this happen. Append a point wrangle. And let's call this lookup curve view, like so. And then open the expression editor. And we will want to look up attributes from a different geometry stream, so we have to wire it into the second input. And this will be the geometry just before the poly extrude, the original splines. Put this into input 2 and make the point wrangle visible. Now let's write some code. We want to use a prim_uv function to sample the curve u attribute, and for this to work we need the target primitive and a UV coordinate. But in the context of the prim_uv function, this UV coordinate is not a UV coordinate as we know it from texturing, but it is a barycentric coordinate. In case of a polyline, it's just the location along the spline. So only the u component is relevant. So let's first create an integer variable called tar_prim. And initialize it with -1, because at the moment we don't know any tar_prim. And then we need a vector, and let's call it tar_uv, and let's initialize it with 0. Like so. And now we want to use the xyz_dist function to find this tar_prim and tar_uv. The xyz_dist function finds the closest location on a primitive, and that's exactly what we need here. So float dist is xyz_dist, and I assign this to the variable dist really only because return the value. I won't use the value anymore. And now I give it geometry stream 1 because it should look for the primitives in geometry stream 1. It should look up the position P, which is the currently processed points position, and then it should please write the results to tar_prim and tar_uv. After this function call, we have now filled tar_prim and tar_uv with values that we can use in a prim_uv function. And we create an attribute curve view on our points here and fill it with prim_uv. So we look it up on the original primitives. Again, geometry stream 1, because we want to use prim_uv on the original splines. We want to look up their curve view attribute, and we want to sample it at the primitive tar_prim, and along this primitive at the location tar_uv. So this code gives us the curve u attribute at the closest location on the original primitives to the current points. That is exactly what we need, because this attribute can be used to sort the points in the correct order. Click apply and accept, and let's move on. To rebuild the primitives, I want to use built-in SOPs, the sort SOP and the add SOP. And that means that I have to use a for each loop to go through all the primitives. So create a for each loop. This gives us 2 nodes, a block begin and a block end node. And the for each runs over an attribute. That means for every iteration it uses the geometry with one attribute. And this attribute can be set on this block end node. It's the piece attribute. In our case I will use class, because class is what I wrote to the points with the connectivity earlier. That means that the for each loop will execute for all points at once that used to belong to one primitive. Let's connect the whole loop. And now we create a sort. But before we append it, let's switch here to points, because the class attribute is on points. And before we append it, let's click single pass and move to pass 1. And you see that we have this loop here. That are all the points that used to belong to one primitive. They have all the same class attribute. That's why the loop executes them in one iteration. And you see the point order of these points here. Now I put the sort SOP in the middle, and I use point sort by attribute, and the attribute I want to use is curve u. As soon as I put this here, the order of the point has changed. The order is now the same order as the original primitives, just because it uses the curveView attribute, and the curveView attribute increases along the original primitive. And as we looked up the curveView from the original primitives, we now have the correct order to all these points. So without the sort, wrong order; with the sort, correct order. And now I can just append an add sub here as the next node, go to polygons by group, and it will just add in a new primitive using the right point order. And I have now a clean primitive. If I go to the geometry spreadsheet, I can see I have one primitive, and if I have a look at the vertices, you see that I have one vertex per point, and the points are all in the correct order. I have now a clean primitive. Let's go to the block end again and tick off single pass, and this gives us new primitives for all our cut loops. Finally, it's time to do our projection. We prepared everything perfectly, and now we can project our knitting loops to the 3D surface. We do so using a VOP, a point VOP. The first input will be our loops, and the second input will be our UV geometry. So this will be this here, the transform to UV. This will go into the second input, because we need both geometries to do the gathering. This will be the first of two VOPs, so we call it UV-Def for UV-Deformer gather info, because here we will gather the necessary information. Later we will use it in a second VOP. Dive inside. The first thing we want to create is a intersect node, because this can be used for ray tracing. And we want to use the current geometry to make the rays, but we want to intersect the rays with the geometry that comes in the second input. So connect the intersect to the second input geometry. The intersect expects two vectors, a ray origin and a ray direction. The ray origin is the 3D world point where the ray should start, and the ray direction is just a vector telling it how long it is and in which direction it should shoot. So for the ray origin, I want to use a position, but to make sure that this does not fail, I will add a little correction vector. So put an add in the middle and then create a constant of type vector, and I just add a vector of 0, 1, 0 to it to make sure that I move my ray origin just above my loops here. And then just create a second constant of type vector and make it 0, minus 10, 0 for the ray direction. Minus 10 makes sure that it goes just down Y and is long enough to always hit something. And this will give us some info. It will return the primitive that the ray hits and the UV. And in this case, again, this is not texturing UVs, but barycentric coordinates. And this is the info we will need to later on use a primuv function to find the 3D points. So we will store this with a bind export. Create a bind export. The first one will be of type integer, and we call it tarprim, and give it the output of the prim port. And then we create a second one, another bind export, this time of type vector, call it taruv, and give it the output of the UVW port. Now we stored the information that we gathered with the intersect on point attributes. And now finally comes the last step, the last point VOP. Append another point VOP and call it UV-Deform. And this will need two geometries again. The geometry to deform, this is our loops, and then the original geometry we want to deform to. And that is the vertex split node basically. or you can use the normal node, it's the 3D geometry before we transformed it to its UV map, because we want to gather the original positions to deform to these positions. So dive inside, and inside we want to use the info that we generated a second ago. So create a bind node and bind the parameter tar prim. Don't forget to set this to integer, and then another bind to bring in the vector information of tar UV. And now we can use a primitive attribute function that is primuv. The vector function is called primuv, but the node is called primitive attribute. And that can be used to use this information here to sample any attribute on the original geometry. That means that this will look up the geometry that comes in on stream 2, which is the original ball. The primitive to sample is tar prim, the UV to sample is tar UV. And the attribute to sample is not CD, which is the default, but P. We want to sample the position. And if we now wire this into position, our knitting loops are gone, because they are where they belong. They are on the surface of our ball. So we finally accomplished our goal and deformed our clean loops to our ball. There's just one little flaw, because all the loops are now flat on the surface. That's because it's sampling from two-dimensional space the three-dimensional position, and that means that the Z information is lost. We have to add it in here, and we will use the normal to do this. Remember that we added in a normal node at the very beginning of this tutorial? Well, it's set to vertices because this is a standard, but set it to points. We need point normals on the original geometry. Like so. That's great. And now we can use these point normals to add in the lost Z information. To do this, we want to use the position from the incoming loops. And we want to split this position to floats. So vector to float, because we are only interested in the Y component. The Y component of the incoming loops is the magnitude of the depths, basically. But we don't want to transform this in Y anymore, but along the normal. So let's multiply the normal by this value. First, we need the normal. We can get the normal by doing exactly the same as with the position. Duplicate the primuv, but instead of gathering the position, let's gather the normal. That means out of this node comes the normal of the original geometry. And if we now multiply this normal by the Y component of the incoming loop position, this gives us back the Z component. And we just add this normal vector to the result of the P gathering, and you see this gives us back the depth of our knit. One level up, let's add a polywire. Make it visible, and let's make it a little smaller regarding the radius, and then append another normal for it to get better shading. And now I switch to smooth shaded and give the polywire more divisions, let's say 12. And you can see this is a beautiful result of the UV deformation. We create the knitting in 2D and then we transform it to the 3D ball. Now you ask, why did I gather the information in this swap and then use it in this swap? It would have been easier to do it just in one swap. That's right. But for performance reasons, I split this, because now what I can do is I can use a ROP output driver, write out the geometry including all the necessary attributes here to disk, and then just use a file node to bring it back in and use this written out cached geometry to do the deformation. By doing so, I keep the whole chain from executing, because this is all preparation work. It has to be done only once, and the ball is animated. So if I move the timeline, it's quite slow at the moment because it does all the cutting and preparation work for every frame, although it works. And if I write it to disk first, it will be a lot faster. I quickly did this, wrote this out to my hard drive and brought it back in, and now you can see that it performs in real time. So no more waiting, and it still works. And by doing this, you can use it on multiple objects without any problem. Of course, the polywire will need a little bit of time, but it's a lot faster than doing all the preparation all the time. So this is a UV-Deformer setup. It's not only useful for knitting, it's useful for a lot of things. I might turn everything you've seen here into a digital asset because it's good to have this handy for a lot of tasks, but especially for knitting, it's really a very useful technique. Thanks so much for watching. If you want to know how I achieved the result you saw in the artwork, please refer to the scene file I attached below this video. I hope you learned something, and see you next time.